Welcome. Today we are diving into the third layer of the Open Systems Interconnection, or OSI model, the network layer. We'll explore its key functions, including routing, Internet Protocol addressing, and packet forwarding, to understand how data finds its way across networks. Let's begin with an overview of the network layer. Firstly, it provides logical addressing and routing, ensuring that each device has a unique address for identification. Secondly, it handles packet forwarding between different networks, enabling seamless data transfer. Thirdly, it enables end-to-end communication, allowing applications to communicate regardless of the underlying network infrastructure. And lastly, it determines the optimal path for data delivery, ensuring efficient and reliable communication. The network layer has three primary functions. The first one is logical addressing, which assigns unique Internet Protocol addresses to devices, enabling identification and location of hosts on interconnected networks. The second one is routing, which determines optimal paths for data packets to travel from source to destination across multiple networks. And the third one is packet forwarding, which moves packets from one network interface to another, based on routing decisions and destination addresses. Internet Protocol addressing is a fundamental concept within the network layer. There are mainly two versions of Internet Protocol addresses: Internet Protocol version 4, also called IPv4, which uses 32-bit addresses expressed in dotted decimal notation, such as 192.168.1.1, and Internet Protocol version 6 or IPv6, which uses 128-bit addresses using hexadecimal notation with colons as separators. These addresses can be categorized as public or private, where public Internet Protocol addresses are globally routable, and private Internet Protocol addresses are used within local networks. This slide shows the structure of an Internet Protocol version 4 address and an example of an Internet Protocol version 6 address. Subnetting is the practice of dividing a network into smaller logical subnetworks. This helps with efficient Internet Protocol address allocation, improved network security through segmentation, reduced network congestion by containing broadcast traffic, and simplified network management and troubleshooting. On the right, we can see some examples of classless inter-domain routing, also known as CIDR notation. For example, 192.168.0/24, which corresponds to 255.255.255.0, provides 256 addresses. Routing is a critical function of the network layer, involving the determination of optimal paths for data packets. The diagram shows how packets can be sent between networks using routers. Here we'll explore two main types of routing. First is static routing, which involves manually configured routes that specify the exact path a packet must take to reach its destination, requiring administrator intervention to adapt to network changes. Second is dynamic routing, where routers automatically exchange network information using protocols like Open Shortest Path First, Enhanced Interior Gateway Routing Protocol, or Border Gateway Protocol to adapt to topology changes and determine optimal paths. Let's explore some key routing protocols. First, we have Routing Information Protocol, or RIP, a distance vector protocol that uses hop count as a metric with a maximum of 15 hops. It's simple to implement and suitable for small networks, but it has slow convergence time and broadcasts updates every 30 seconds. Next, we have Open Shortest Path First, or OSPF, a link state protocol that uses cost as a metric based on bandwidth. It offers fast convergence with Dijkstra's algorithm, supports variable length subnet masking and route summarization, and features a hierarchical design with areas. Finally, we have Border Gateway Protocol, or BGP, a path vector protocol used for inter-autonomous system routing on the Internet. It makes routing decisions based on network policies, uses Transmission Control Protocol port 179 for reliable communication, and supports classless inter-domain routing and route aggregation. Packet forwarding is the process of moving packets from one network interface to another, based on routing decisions. Here are the typical steps of packet forwarding process. Number 1, the router receives a packet on an interface. Number 2, it examines the destination Internet Protocol address in the packet header. Number 3, it consults its routing table to determine the best path. Number 4, it updates the packet's time to live, also known as TTL, and recalculates the header checksum. And number 5, it forwards the packet out the appropriate interface toward its destination. The diagram on the right illustrates the structure of a packet, highlighting the Internet Protocol header and payload data. Here are some key network layer protocols. First, we have the Internet Protocol, or IP, which is the fundamental protocol of the network layer that provides addressing and routing for packet delivery. It has Internet Protocol version 4 and Internet Protocol version 6 versions, is connectionless and offers best effort delivery, and handles fragmentation and reassembly. Second, we have the Internet Control Message Protocol, or ICMP, which provides error reporting and diagnostic functions for Internet Protocol. It is used by the ping and traceroute commands, reports network errors and congestion, and includes echo request or reply, and destination unreachable features. Third, we have the Address Resolution Protocol, or ARP, which maps Internet Protocol addresses to media access control addresses on local networks. It maintains an Address Resolution Protocol cache of Internet Protocol to media access control mappings, broadcasts requests and unicast replies, and is essential for last hop delivery. Finally, we have the Internet Group Management Protocol, or IGMP, which manages multicast group memberships. It enables multicast communication, allows hosts to join or leave multicast groups, and is used for streaming and video conferencing. In summary, the network layer provides logical addressing through Internet Protocol addresses. Routing determines optimal paths for data delivery across networks. Packet forwarding moves data between networks based on routing decisions. Subnetting divides networks into smaller, manageable segments, and key protocols include Internet Protocol, Internet Control Message Protocol, Address Resolution Protocol, and various routing protocols. In the next module, we'll move on to the fourth layer, the transport layer. We will discuss the Transmission Control Protocol and the User Datagram Protocol protocols, connection-oriented versus connectionless communication, flow control and error recovery, and port numbers and socket addressing. If you like this video, hit that like button and don't forget to subscribe. Visit codelucky.com for more such useful content.